combinations of functions, composite functions. The goal in this section is really to show you that sometimes we can look at a function, and if you look at some of them, they look like there's a function within a function. It's like there's several things going on at one time. If you've noticed that in the past, then you've noticed correctly that typically there are things that are working on the inside. And sometimes it almost seems like what's working on the inside seems to almost work against the results of what you're actually trying to get with the particular function. Well, it's not actually working against anything. It's just what we call a composite or a composition of functions. That is that we may have a function contained within another function. And it doesn't have to just be two. It could be three or four. It could be several things going on. And when that happens, obviously things get more complicated. But that's not the idea. Is to show you the complexity of the function, is really to show you the simplicity of the function by understanding in terms of what's happening with this function contained within another function, if that's the case. Now, the overall goal of this section is to actually show you that in doing this composition, to actually be able to see an embedded function within a bigger function is to eventually be able to reach our hand in and pull that function out and let that inside function represent the outside, almost like a caterpillar and a butterfly, that in its beginning it's the caterpillar, but actually we understand that the butterfly itself is contained within that caterpillar, and so it just takes time for the inside to work itself out and then the outside to work itself back in. What am I saying? Eventually we'll talk about an inverse function. So the inverse function, if a function has an inverse, that really means that the inverse is embedded within the function itself. I want to be able to pull it out and whoa, look at that. What is that? That's this inverse. And so we could talk about very neat properties of inverse functions in terms of what that means and what that can do later on. So today, just to give you the idea of where we're trying to get to, that we're actually trying to get somewhere, is we have to talk about this idea of a function composed within another function. Well, we do that by first talking about the idea of domain and range. That's not new. We've been talking about that. But as we go on in this class, we want to try to refine that to make sure you understand. Now, please, say for example, when you get your test back, if there are any mistakes that you make, go back over that information and make sure you work on that. Make sure you get that so that as we move along, you will definitely understand. And that's okay. Look, the idea about class is that we're all works in progress. And so it's okay to mess up, but my hope for you is that in messing up, that you go back and you see what your mistake is, and that you actually learn that for that next go around. Because a lot of these things we kind of see over and over again. If you need help, by all means, the Star Center or talk with me so that we can set you on the right path. So here was a comment that I wanted to make with respect to the domain and range before. I kind of said it, but I want to make sure that that you see it and that you can touch it, and I understand in terms of how we learn things, especially when it comes to math. If somebody says something, that don't mean we got it. It may sound good, but things like math and science, you have to hear it, but you have to also see it. And then a lot of times you have to rewrite it yourself. And then sometimes you have to speak it just to make sure that you have all of the perceptions working so that you can retain knowledge. So here, the domain, and I'm about to stay here. I went back and listened to the other recording, and when I step over to the screen, the volume of the mic doesn't pick that up. We used to have a lapel years ago, and we could kind of walk around and talk. But anyway, so the domain, I call this, it's the set of the x values that corresponds to the graph. So in just thinking about that intuitively, look at the graph with respect to the x-axis to map out the domain. Sometimes it's easier to look at the points that makes the equation or function undefined. Excluding these points yields the domain. That is, that where are the problem children? If I can kind of pinpoint the problem children, then I know that all the other children are okay. Well, I don't know, because when I was coming up, I was probably one of those problem childs. But anyway, but that's one way in terms of how we do it. The range are the y values that define the graph of an equation. I make mention, first of this idea of a graph, but what if you don't have a graph? And so you have to kind of still be able to get the domain and range. So intuitively look at the graph with respect to the y-axis to map out the range. The range values, they depend on the x values. They depend on the domain. So here are some problems, some examples in terms of finding the domain of a function. The question that I have on the side, what are the restrictions? That's going to be the key in terms of those areas that we say will not define the function or the equation, the problem children, if we could say it like that. So how do we determine the restriction with respect to a domain? We want to look at the problem, not just math problem, but like the problem. Like, what's your problem, right? So if it's a fraction, the problem for fractions will be where the denominator is 0, because that's undefined, right? That's the problem. I cannot divide by 0. I can't say 5 divided by 0 because we don't know what that is. It would say it's undefined. It's not 0. So if I have a fraction, then I must set my denominator equal to 0 and solve for x. Those values for x, we say we have to exclude. And then all the other points, again, look, got a room of kids. Where are the problem kids? If it's just one, let's find him or find her. Then hopefully we say everybody else should be okay. Okay. So that's the idea here. So if it's a fraction, look at the denominator, set it equal to 0. Those x values you want to exclude. Now it's going to be this example here for this problem, but let's look at the other restrictions. If the expression is a radical, if it's a square root, then I'm going to set what's in that radical or under that radical, set that greater than or equal to 0. Simplify that becomes my domain. Okay. If the expression is a polynomial, like a quadratic or a cubic equation, if it's just straight polynomials, then automatically our domain would be the set of all real numbers from negative infinity to positive infinity. Now, so for this problem, do you see the problem? Notice here that x plus 3 cannot equal to 0, right? Because if x plus 3 was 0, I would have 12 divided by 0. So we note here that x plus 3 cannot equal to 0. Well, this implies that x cannot equal to negative 3. So on the number line, we're going to exclude negative 3 and include all the other numbers. That's our domain. So our domain, if we look at the number line, and we're going to write this, it says to write this in interval notation. So that means that we're going from negative infinity, comma, to negative 3. We put a parenthesis because the parenthesis says do not include that number. It's everything about that number. Union, parentheses, negative 3 to positive infinity. Okay? Are you with me? All we've done simply was to say that our domain is all real numbers except negative 3. That's what that means. Okay? The domain, all real numbers except negative 3. That's how we write it out with respect to interval notation. So that's interval notation, and so that's that. Any questions there? And so in my math lab, or my lab math, or whatever the heck they call it now, that's just how it looks if you get it right. And they give you a few tries, so if you get it wrong, they give you another try. I think you can have like 3 attempts, and then after that, they change the problem up. Basically, it's the same kind of problem, but it just changed that one up for you. Find the domain of the function. My question, what are the restrictions? Well, and then one, what's the restriction? But then also, can we identify the function? Now, I talked about earlier, in terms of the restriction, is it a fraction? Okay, and so then we deal with that. Is it a radical, like a square? Here, when I talk about even roots, excuse me, I'm country and southern, so sometimes that comes out. That simply means that this radical term has to be even, like the square root, the fourth root, the sixth root. If it's an odd root, it doesn't matter. What's inside the radical can be negative or positive. So there's no restriction, right? So here, I can have the cube root of negative 2. This guy is defined. But the square root of negative 2, see this? Undefined, or we define it now as being imaginary, right? But it's not real. So that's what I mean by this even root. So is the function, the problem that I'm given, is it a fraction? We call it either fraction or rational. Just another word for fraction. So is it a fraction? That is it rational? Is it a radical, like a square root? Or is it a polynomial? So those are the 3 that I'm expressing here, 1, 2, 3, for these restrictions. So this guy's not a fraction. It's not a radical, right? So this is a what? Who? I didn't hear you. Somebody said something. Polynomial, right? Respect. Polynomial cracker. What you say, Emmanuel?
I wanted to say that, but I thought it was wrong.
Say it, man. Look, again, folks, this is the laboratory. We can mess up. It's okay. So we mess up. I help you get it right. We move on. We learn something about life, right? So this is a polynomial. If it's a polynomial, there's no restrictions, right? So here, my domain, all real numbers. polynomial. If you get it wrong, I will not bite your head off. Won't do that. Polynomial. All right, what's the domain here? What's the restriction? What is this kind of fraction? I mean, what is this kind of function? It's a fraction. Okay, right, it's a fraction. So that means that my denominator can't equal to 0. So what we're going to do here is just say, okay, when is x squared plus 14x plus 48, when is that 0 or not equal to 0? Doesn't matter. Can we factor this? X plus 6 times expression x plus 8. Two numbers that when you multiply we get 48, but when you add them you get 14. So 6 times 8, 48, 6 plus 8, 6 to 14. Good. So you get x is equal to -6, x is equal to -8. So this means that my domain has to exclude those two values. Do you see that? Because those two values make the denominator 0. That's a uh-oh. So we say our domain, and we're looking at the number line. That's all we're doing. And every time for the number line, we're always going from the left to the right, least to the greatest. So the number that comes up first on this number line is -8, then -6. So I'm going to write my domain in that fashion. From -infinity, I get to -8. Parentheses, union, parentheses, -8, I get to -6. Close that up. Union with -6 all the way to positive infinity. Are you with me? Okay. Now here's the thing. You know, the thing about math is it's not our first language. And because it's not our first language, just because somebody else can do it pretty good doesn't mean that I can. Even watching them, and they're doing a good job, and you know, oh, that's so. It's like listening to a song. You know, you listen to a song and you think you can sing like Kelly Clarkson. And sometimes if you turn the volume up pretty loud, you think you sound like Kelly Clarkson, but you don't let that speaker go out. Or them good folk in church, because they'll sure tell you, buddy, you know, maybe you might want to consider being an usher. You know, so. Pardon me? Don't quit your day job. Exactly. So in terms of trying to get that song, you have to listen to it over and over again. You got to sing it over and over again. You got to keep rehearsing and practicing. It's the same thing with math, because math is not our first language. So just because you know some teacher does a pretty good job doesn't necessarily mean that when I get by myself it's going to be the same way. So what I'm saying is, like, when you leave class, if you have time in that day, just go take a stab at the homework in my math lab. Just take this. I mean, you can, even if you don't get them right, just play around with it, so you kind of get something on your mind. You know, right then. You saw somebody talk about this. Let me go and just kind of play around with a few problems. And then maybe that night or later on that week when you have more time, you can kind of, you know, refocus and regroup. That's fine. But just kind of put it on your mind as often as you can. All right. Class assignment. All right. This one's for you. What's the domain? Is that what you got for the domain? Just excluded negative 15 and negative 4? Right. Who tried to combine those two fractions? Like, did you add them and do all the least common denominator? You didn't have to, right? I mean, if you did that, I mean, you still end up with the two problem children would be negative 15 and negative 4. So just make sure that when you list those numbers out for that domain, that you put the numbers in the correct order. You're always going from the least to the greatest. Because if you, say for example, if you got the negative 4 where the negative 15 is, the computer's going to mark it wrong. And you may say, I got the numbers, but they're not in the correct order. Right? So order is significant. Because if the order wasn't important, then when the authorities come to your house and they say, you know, who's the oldest, the responsible person in your home, you can't get the 5-year-old, right? You got to get the 25-year-old or the 35-year-old. If not, if you say, okay, it doesn't matter how we order these numbers, then it doesn't matter how we order even in terms of significance when it comes to age as well, because these numbers mean something. Is that okay? Does that make sense? Okay. All right. What's the restriction here? Talk to me. Ma'am? Radical? Is that what you said, radical? Yep, radical. Very good. Kind of hard to, talk with these masks on, that kind of thing. I understand. Yep, you're exactly right. It's a radical. So I'm going to set, and it's a even root radical, right? Square root. So I'm going to set what's in that radical greater than or equal to 0. So we say this implies, I need to change the color up, I think, maybe, because I think what happens is some people have certain colors are not good. So we say x plus 10 is greater than or equal to 0. I mean, in a nutshell, that is the domain, but we're going to, by all means, get the x by itself. So we say this implies that x is greater than or equal to negative 10. Now, if they ever ask to write it in set notation, which they won't because it's too much for the computer, but set notation is this. It's the set of all x such that x is greater than or equal to negative 10. But for let's look at the number line. Here's the number line. So we find negative 10 on the number line. And it's everything greater than that. And we put the circle in on that because we can include the negative 10. So our domain is a bracket, negative 10, comma, all the way to positive infinity, parentheses. Okay. The bracket means include the endpoint. Parentheses means we do not include the endpoint. All right. What are the restrictions here? And there's 2 of them. What are the restrictions here? There's 2 of them. All right. What's one of them that you see? It's a radical, right? So it's a radical. That means that x minus 12, that has to be greater than or equal to 0. What's the other restriction?
It's a negative.
Huh?
It's a negative.
What's negative?
The 12.
That's not a restriction. I mean, 12 can be negative. It's fine. It's just that sum or that difference has to be positive, right? X minus 12 has to stay positive. That's fine. What's the other restriction? It's a fraction. That means that my denominator cannot be 0. Got to get that. So the first is that it's a radical. So we know that from here, x minus 12, we say it has to be greater than or equal to 0, but the other thing is that it's a fraction, which implies that that denominator cannot equal to 0. Well, that implies, put 1 and 2 together, that just implies that x minus 12 has to be greater than 0 and not equal to. Does that make sense? So that's all we're solving for. And this, yes, implies that x is, I'm just adding 12 on both sides, x is greater than 12. So my domain goes from, x greater than 12, everything bigger than 12. So that's parentheses 12, comma, positive infinity. On the number line, we have a circle. Does that erase? Oh, it erases the whole thing. That's dull. Straight line, straight line. So we find 12 and everything bigger than it, right? That's going to plus infinity and beyond. So later on, from here on out, if you have a radical, if that radical is downstairs in the denominator, we just set what's in the radical just for here greater than 0, right? So this, we say, this just implies, just cut right to the chase, x minus 12 is greater than 0, and then we get x by itself. Don't leave me, don't leave me. Did y'all remember that was it TikTok, when TikTok first came out? They Does anybody watch TikTok? Okay. Do you remember when it first came out? It had some short little videos, and the people would say at the end of whatever they would do, they would say, "Don't leave me, don't leave me, don't leave me." Anybody remember that? That was like 2020. It was like right when the pandemic came out, and then, well, my wife can tell you all about that stuff because she's like a TikTok. I think she's addicted to it, And I'm like, that's not good. But who listens to husbands, right? Adam and Eve. Anyway, the algebra of functions. Y'all don't know my wife, do you? Anyway, the algebra of functions. Sum, almost said slim, but the sum, difference, quotient, and the product. So with functions, the way we have numbers, we can apply the same operations. You add numbers, subtract numbers. Likewise, you can add fractions, subtract fractions. You've been doing this all your life. Likewise, we can multiply fractions like we multiply numbers. We can divide fractions the way we divide numbers. Same thing about division of numbers. I cannot divide by 0. So that last part, number 4, provided that g of x is not the 0 function or that g of x is not 0. Cannot divide by 0. Well, that's that. Who cares, right? So let's move on to what we do really care about. You don't, but no, I'm just joking. It sounds like the guy when I went to, this was years ago, like maybe 18 years ago. I got a ticket and I didn't want the insurance to affect the points to affect my insurance. So I went to the class. So we had a really cool teacher, and so he kind of taught like that. He was like, okay, let's talk about this point right here. You don't really care about it, but I do. But oh man, we love that guy. And then we got down to the end, he gave us all the answers, and we were like, hey, we're gonna give you a tip, right? No. Oh boy. So the composition of functions, the composition of a function f and g. That's what I was telling you in the beginning, how we have a function within a function. So that's all this means. So f composed with g. Look, folks, and I know math is not our first language, but please don't leave here and we talked about frogs. But anyway, or fog or whatever. Okay, bad math joke. But anyway, so f, that little o is the composition term or operation or operator. It simply means f composed with g. What does that mean? That simply means that g is acting like a number with respect to the function f. So f composed with g is f of g of x. If you go in the other direction, that's fine too. If we have, well, got that already. If we have g composed with f at x, so this is g of f of x, right? The domain of the composite function of f composed with g is the set of all x, such that x is in the domain of g and g of x is in the domain of f. Okay, what does that mean? Let me see if I can explain it. And I think I have the explanation of that. We have a problem where they give you the composition and they ask you to find the domain for that, and I put a statement there when we get to that problem to help you out. But here, let's just do the composition. So part A, we have f composed with g at x. This is f of g of x. Here's how we're going to do it. So I'm going to write that function g of x inside of the parentheses here. Replace g of x with what it is. This is x plus 2. Okay. I do this for all the composition functions. That is what I do. You do likewise. Okay. So I replace that g of x with what it is. G of x is x plus 2. Now the function f says, he says, whatever you give me, multiply it by 9. Doesn't matter what it is. Whatever you give me, multiply it by a 9. But I'm giving you x plus 2. So I'm going to say 9 times parentheses x plus 2. Right. And so that's 9x plus 18. Is that okay? So again, f composed with g of x, by definition, this is f of g of x. That's what that means. F composed with g is f of g of x. That is that inside of the function f is this function g. There's a function inside of a function. So all I've done here was to replace g of x with what was given. G of x is x plus 2. This is f of x plus 2. And then I look back now, f says whatever you give me, it's an operator. You give me something, and then it does something to it to get something new. So f says, whatever you give me, I'm giving you this term x here. That's the same x here. I'm multiplying it by 9. But here, I'm giving you x plus 2. So I'm multiplying x plus 2 times 9. Now part B, they reverse it. G composed with f evaluated at x. This is g of f of x. So now I'm going to replace the f of x with 9x. So this is g of 9x. So g says whatever you give me, that's this guy right here, add a 2 to it. Whatever you give me, add a 2 to it. I'm giving you 9x. 9x plus 2. Okay. So now part C. Part C says just take what you got, the results from part A, and just plug in 2. So f composed with g evaluated at 2. This is f of g of 2. Well, since I got over here this 9, and the way I do it, I typically try to go right back to this term here. This is 9 times, this is 2 plus 2. Right? 36, or just 9 times 4, right? You can plug the 2 in here, it doesn't matter. You can plug the 2 there, or you can plug it there. You still get 36. Part D. G composed with F, evaluated at 2. This is G of F of 2. So look at part B. That just becomes 9 times 2 plus 2. That's 20. So this is a pretty good exercise so that you can kind of conclude that F composed with G evaluated at X is not always equal to G composed with F evaluated at X. Right. Not always. There's a rare case that they will be equal. When that happens, that's where we get the goal. That is, we get the inverse function. Right? That's like what we're trying to get to. Let's look at another one. Okay, that was just the answers for that one. We got that. Okay, what about this one? So part A, F composed with G evaluated at X. We said this is F of G of X. So I'm going to replace the G of X with what it is. So this is F of X squared minus 4. So F says whatever you give me, square it, and then add 7 to it. F says whatever you give me, I'm going to square it. Well, I'm giving you X squared minus 4. Square that, and then plus 7. And here I say expand the results, right? Just work that out. So we're going to, you got to FOIL that out. So it's X squared minus 4 times X squared minus 4 plus 7. So this is the first time the first, X to the 4th. Outer times the outer is minus 4x squared. Inner times the inner is minus 4x squared. So that's minus 8x squared. They're like terms. The last time the last is plus 16 and then plus 7. So this is x to the 4th minus 8x squared plus 23. Part B, G composed with F, evaluated at X. This is G of F of X. So now I'm going to replace F of X with what it is. F of X is X squared plus 7. So this is G of X squared plus 7. So G says whatever you give me, square it, and then minus 4. I'm giving you this x squared plus 7. Square it, minus 4. Now expand that out. So we do the first term the first, outer times the outer, inner times the inner, last time the last. So we get x to the 4th plus 14x squared plus 49 minus 4. So that gives us x to the 4th plus 14x squared plus 45. Part C, F composed with G evaluated at 4. So this is F of G of 4. Now it's a couple of ways of getting that, and please don't let me complicate you by showing you, that first method of getting the actual evaluation of the point. Part C goes back to part A. Basically, wherever I see an X, I'm going to put the 4 in and then just do the evaluation. So this is 4 to the 4th minus 8 times 4 to be squared plus 23. And you simplify that. think I did that over here. Yeah. You get 151 when you plug that information in, just on your calculator. Let me change the color. If you wanted to, you could have done this. Since this is g of 4, I can go ahead and calculate g of 4. So g of 4 is 4 to be squared minus 4. So this is 16 minus 4. I get 12. And so what this is the same as f of 12. So go back to the function f of x. This is 12 squared plus 7. This is 144 plus 7. And that is 151. Right. Is that all right? Okay. Either way, you get the same thing. So I just showed you two different ways. Hopefully that didn't confuse the crap out of you, right? but if one way is easier, then you do whatever is best for you. I'm fine with that. Part D, G composed with F, evaluated at 4. So this is G of F of 4. So if you want to do it that way that I just shown, so let's just find f of 4. So this is 4 squared plus 7. So that's 16 plus 7, right? So this guy is 23. So this is g of 23. So now I'm going to go to g, and this is g of 23 is 23 to be squared minus 4. So it's 23 squared minus 4. And on your calculator, you get, that'll be 525. 529 minus 4. Okay. Any questions there? Is everybody okay? And here's the thing. You know, here's what I hope is that, you know, like maybe it's okay, but then I think the only way that we get this stuff is that you got to go home or go wherever and you put your hands on it yourself, and that's when you really begin to get it. Ma'am. Oh yeah, thank you. Yeah, minus 4. Yeah, 525. Thank you. All right, and it's just more of the same. If we're okay, can I skip this one? Okay, because this is just a repeat of those two problems there. This is a little bit different here, so let's look at this one. This guy has a radical in it. Okay. Part A. So this is f of g of x. So this is f of, I'm going to find g. G is x minus 3. Now f says whatever you give me, take the square root of it. So this is the square root of x minus 3. Okay. That's it. Part B, this is g of f of x, or well, g composed with f, that's g of f of x. This is g of the square root of x. So g says whatever you give me, I write it here, and then minus 3. So I'm giving you the square root of x, then on the outside, minus 3. These are different. They're not the same. This is not equal to this guy. Okay? So don't just think that you can apply the pencil method and just somehow, you know, say, oh, they're the same. Look, I can just do that. That's not it. No, the pencil method does not work here. Okay. That's for like my calculus 3 where when I make a mistake, I go and just take my pencil and just erase it. But anyway. The famous pencil method. So part C, F composed with G evaluated at 7. So this is F of G of 7. So I find F of G of X. So here, what this simply says is I'm going to replace that X with the 7. So this is the square root of 7 minus 3. We get the square root of 4. That's just 2. Okay. Part D, G composed with F, evaluated at 7. This is G of F of 7. I go to part B. So this is the square root of 7 minus 3. That's the answer. Leave it just like that. Okay. All right. Any questions so far? Okay. Now, I'm gonna show you the trick. I want you to see it first. I don't have to tell you this first. I can tell you this afterwards. I don't know which is helpful. But you see the function F and the function G? Now, I want you to look here. This is minus 6. This is plus 6 over there. So for F of X is minus 6. G of X is plus 6. For F is 4 times X, right? For G is this X term divided by 4. What they're wanting you to see eventually, that one function is the inverse of the other. Inverse simply means operation switch. If something is added over here, something is subtracted over there. Something is multiplied over there, something is divided over there. You compose them together, you get this function is the inverse of the other. So you don't have to see that now. When we get to the section for inverses, that will be explained. That is that F composed with G evaluated at X is equal to G composed with F evaluated at X. This implies that G is the inverse of F. And so we can write then that thus G is equal to F inverse of X. That's later on, but that's what happens when I have the compositions of the two functions. What happens, that really gives you just the identity element, X. But anyway, I digress. Lest I keep you too long. F composed with G. So this is F of G of X. I'm just going just through my regular routine. So G of X is this X plus 6 divided by 4. So this is F of X plus 6 all over 4. But F says whatever you give me, multiply it by 4, and then on the outside, minus 6. So this is 4 times parentheses. I'm giving you X plus 6 over 4. And then minus 6. So this is 4 divided by 4. That cancels out. So I have left X plus 6 minus 6, which is just equal to X. See that? See that? Now the real cool thing about math is this, folks. A lot of it, I'm not teaching you to memorize it. If we do it right and the steps right, then it produces what it's supposed to produce. Right? If you mix that flour and that buttermilk or milk, and eggs and sugar and mix that stuff up right. Put that flavor in there. Put it in the oven and set that oven for the right temperature. It's going to cook by itself. You ain't got to jump in that oven. You'll burn yourself up. See what I'm talking about? See what I'm talking about? That's what math is doing. But see, a lot of times we mess it up. We keep looking in the oven, keep opening. Man, that cake gonna flatten. Ain't no cake no more. You got flat bread. I don't want no whole cake. See what I'm talking about? Let the math do what it's supposed to do. You just do what you're supposed to do. Just each step. Does this one step make sense? Because a lot of times we keep dreaming with math. Dreams ain't true. Just because you had a dream about it don't mean that it's supposed to happen. We do a lot of that with math. I thought I could. Who told you could do that? It just felt like it.
That's what my mama said about stomping in the house when she was spreading leaven.
That's good. That's good. Bless your heart. Part B. Let's not get in trouble. Part B, G of composed with F.
So you want some decent rolls? Because stop keep out on the house.
G of F of X. So here, F of X, I'm going to put it there. It's 4X. So this is G of parentheses 4X minus 6. So G says, whatever you give me, this is G. It's taking that X, it's putting it there. So whatever you give me, I'm going to put it there, plus 6, all over 4. I'm just going to do what it says to do. So I'm giving you, the X now becomes 4X minus 6, plus 6, all over 4. Okay? So let's see what happens. This is 6 minus 6, or minus 6 plus 6, that cancels out. I have left 4X all over 4. 4's cancel. I have left X. They're just getting you set up for the inverse of a function later on. But in the beginning of this, I wanted you to see the reason why they're inverses, right? This is minus 6 plus 6. This is 4 times X. This is this term divided by 4. This is X times 4, if you could say. This is this X term divided by 4. All opposite operations. And it's a composition of that. See how we have a function inside of a function. Have 2 or 3 things going on at one time. Okay. Part C. F composed with G of 5. Look, the result is always just X. So what is X? X is 5. That's it. G composed with F, evaluated at 5. See, 5 is X. Again. That's it. All right. So here, part A, find the composition F composed with G. And then it says find its domain. I give the note here. The domain of F composed with G is itself with the restriction of G, because G is going to be inside of this composition. Remember, this is F of G of X. I know for G, the restriction would be that X cannot equal to 0, right? Right there. See that? X cannot equal to 0. But I need to simplify F composed with G. So this is F of G of X. This is 1 over X. Okay, so F says, whatever you give me, you put that term here. So this is 7 all over 1 over x plus 7. We simplify. This is 7 over, I'm adding two terms in the bottom. Two terms, they're two fractions. This is 1 over x plus, this is 7 over 1. I need to make its denominator x. So this is 7x over x. Because 7x divided by x is still 7. Where did I get the x from? I looked at this x here. I looked at that term, and I want that term down here as well. So if this was 1 over 3, I would say 7 times 3 divided by 3, right? So it's just same good old-fashioned adding two fractions. So this is 7 all over. If I have two fractions, if they have the same denominator, I can combine the numerator. So this is 1 plus 7x all over x. And then if I have a complex fraction, you remember that if you have a over b divided by c, this is understood to be a over b divided by c, and this is a over b times this a divided by b over c. So this is a times c all over b. So this is this 7 divided by 1 plus 7x all over x, which is 7 times x all over 1 plus 7x. Remember, this is the complex fraction from many years gone back. So this a represents the 7, the b represents the 1 plus 7x, and the c represents that x there. So this is a divided by b over c. So remember, if we have division, we change that to multiplication, and we invert the second fraction, right? So that becomes c over b. Very good. So what this says is that my denominator here cannot equal to 0. So 1 plus 7x cannot equal to 0. You solve for x there, we get 7x cannot equal to -1, excuse me. And this is x cannot equal to -1 over 7. So I have two restrictions. Also have the restriction from g of x is x not equal to 0. X cannot equal to 0. So on the number line, I list these numbers in order. Well, from the left to the right, I get to -1 over 7 before I get to 0. So I have everything else except those two numbers. So this is negative infinity, positive infinity. So f composed with g, let's write that out. Make sure we get that correct. F composed with g. Evaluated at x. This is, we got that to be 7x all over 1 plus 7x. And then its domain. The domain is the exclusion of the restriction for g, because that's what the this definition tells us. The domain of f composed with g is itself. What does that mean? Well, that's this guy right here. That's what I get when I find f composed with g. I find its domain, that is everything except -1 over 7, with the restriction of g. The restriction of g is x not equal to 0. So the domain here would be
parentheses, negative infinity, I get to that negative 1 over 7. Close parentheses, union with negative 1 over 7 to 0. Close that up, union with 0 to positive infinity.
Yeah. So I want to put that, I mean, it's a homework problem, but I want to make sure I go over that because here's the thing. I would have personally, just without knowing that, I would have found this F composed with G, and I would have said that my domain is just everything except negative 1 over X. I wouldn't have thought about this restriction of G. The reason why is that F is treating G as a number. So so G then becomes the domain of this composition. So I have to also find the restriction of G. G is being restricted by 0 because it's the fraction 1 over X. All right. Well, I got class assignment, but I only have a couple of minutes. Let's go ahead and just work through this. Part A, F of G of X. I think this is the last problem anyway. This is F of X plus 9. So G is X plus 9. F says whatever you give me, take the square root of it. So this is the square root of X plus 9. That's part A. All right. Now G is a polynomial, right? This guy is a polynomial. So its domain would be all real numbers. So basically there's no restriction on G. But there is a restriction on F composed with G. This guy implies that X plus 9 has to be greater than or equal to 0. And that's X has to be greater than or equal to negative 9. Well, since there's no restriction on G, but there's a restriction on F composed with G, my domain for part B is just this guy right here. So look at the number line. Find negative 9 is everything bigger than that and also inclusive of it. So we start at negative 9 and bless you, we go to positive infinity. And folks, I think that should be it.